Okay. Well, thank you very much for the invitation to speak to you today. And I'm very sorry that I can't be there in person. I think it would have been a wonderful experience. Okay, so I'm going to talk about some joint work with Travis Shedler, which is part of a larger project with Travis and with Alistair Craw as well. And I'm going to talk about minimal degenerations for quiver varieties. So you can see the plan here. I'll just give or recall the definition of quiver varieties, even though I'm sure you've seen it several times in the last couple of days already. And then I'll talk about symplectic leaves and minimal degenerations for quiver varieties, describe a bit of the combinatorics behind these, and then most importantly, I just want to give lots of examples so that you can kind of see the different sort of behavior that can happen in these quiver varieties. And at the very end, I'll talk about an application of these minimal degenerations to normality of leaf closures in quiver varieties. Okay, so here's the definition. So as I'm going to fix a finite quiver Q. So we've got vertices Q0 and arrows Q1. I'm not going to put any constraints on it. You can have as many loops or cycles as you like. And I'm going to pick alpha to be my dimension vector throughout. Okay, so of course, from this, you can look at the space of representations of your quiver of dimension alpha. And this is acted on by the group G alpha, which is just the product of the general linear groups at the vertices. And of course, the thing that we really care about is that from this, you get an action on the cotangent bundle to this space, which you can identify with representations of the doubled quiver Q bar. And the key point is now that this is a Hamiltonian action. And so you have a moment map mu, which goes from the space of representations of the doubled quiver to the Lie algebra of your G. Okay, so that's the setup. And then we just perform Hamiltonian reduction to get the quiver variety. Okay, so these are Nakajima quiver varieties. And as I said, it's just Hamiltonian reduction. So you take the preimage of 0 under this moment map, and then you quotient by the action of G. Okay, and so formally, this is just spec of the invariant ring for the action of G. And the key thing for us is that these quiver varieties, they have symplectic singularities. So in particular, that means that the Poisson structure is generically non-degenerate, and the quiver variety will decompose into a finite union of symplectic leaves. And each of these symplectic leaves is smooth, connected, locally closed inside my quiver variety. Okay, and so what we want to do is somehow understand the relative singularities with respect to these symplectic leaves. Okay, so that's that. And so what do I mean by minimal relative singularities? Well, this is the idea of minimal degenerations, which you've probably heard about already in the last couple of days. So if I take a pair of leaves, then when I take a closure of one leaf, it's a union of leaves. And so I can look at a leaf that's contained inside the closure. And I'm going to say that this pair is a minimal degeneration if there doesn't exist an intermediate leaf. So there's no leaf properly sitting in between the closure of the larger leaf and this smaller leaf. Okay, so nothing in between. And so whenever you have these minimal degenerations, you can take a slice to the smallest leaf and intersect it with the closure of the bigger leaf. And because it's a minimal degeneration, that will be singular, but it's an isolated singularity. It's only singular where it intersects that smaller leaf. Okay, and of course, this is exactly the same as has been done classically for nilpotent orbit closures. And the result that I'll talk about next that it most resembles is this result by Malkin, Ostrich, and Vibronov, where they classified these minimal degenerations for affine Grassmannians. Okay, so as you might expect, the situation for quiver varieties is very similar. Okay, so they're the things we're interested in. We're interested in classifying what are these isolated singularities that appear when you do this for quiver varieties. Okay. And so the sort of main abstract result is that actually there aren't so many isolated singularities when you look at quiver varieties. So they're given in this small list here. So you try to think of all the isolated singularities you can think of that occur as quiver varieties. Well, of course, the first class of examples are Kleinian singularities. The Mackay correspondence tells you that you can always realize these as quiver varieties, and so they have to be on your list somewhere, and indeed they are. The second class of examples is just if you take the minimal nilpotent orbit inside GLN and take its closure, then this is also a quiver variety. So this you can just realize so this, of course, you can just realize as a quiver variety with 2 vertices and n edges between them. So that's also on the list. And then there were 2 maybe slightly more surprising examples. So this one you can realize as Z mod 2 acting just by -1 on C to the 2n, and you take the quotient singularity. But it also occurs as the type C minimal nilpotent orbit closure.
So is this slice symplectic varieties? What kind of geometric structure does this slice have?
Oh, yeah, good question. Yeah, so I should say, I mean, we work étale locally, so these are étale slices. And they're also, yeah, they're all symplectic singularities. So they're, yeah, the thing that's maybe surprising in this list is that these 2 examples do not occur as quiver varieties, right? You can't construct a quiver variety that will give you this or this, because this last example is not normal, and quiver varieties are normal. But they do occur as minimal degenerations between leaves. So that's a bit unusual. And yeah, like I said, so this one is also very special because this is a non-normal example. So it tells you in particular that many leaf closures inside a quiver variety are not normal. And it's somehow the simplest non-normal thing you can write down, really. So I just mean by notationally here, this is just the polynomial, well, this is just the ring you get by taking a polynomial ring in 2 G variables and just forgetting degree 1. Okay, so its normalization just gives you back the whole polynomial ring. Okay, so this is the abstract result. It tells you take any quiver variety, you can frame it or unframed, it doesn't matter. And the minimal degenerations will always be on this list. It's maybe worth pointing out that if you look at the physics literature, they study, somehow they're further ahead than we are. They study Higgs bundles, Higgs branches for quiver gauge theories where the gauge group isn't type A, and they seem to see many more examples of minimal degenerations happening. So this list is maybe small because it's only for type A gauge groups. Okay, so I'll try to explain a bit of the combinatorics behind this result. So if we don't follow any of this part, it doesn't matter really. The important part is the next bit on examples, I think. Okay, so first of all, to this quiver Q, you can associate a root system, so a set of roots, and I'll write R plus for the positive roots of this root system. And the only thing we really need to know is that you have an Euler pairing, an Euler form on this root system, so that when you pair simple real roots, you get 2. And from that, you can define a certain quadratic form, this P alpha, which is just 1 minus a half the Euler pairing of alpha with itself. And then Crawley-Bouvier introduced a certain set. So this is picking out, essentially roots where this P alpha is maximal. And so what you do is you take your alpha and you look at every possible decomposition of alpha into a sum of roots, positive roots, which is a proper sum. And then you ask that when you evaluate this quadratic form on it, it's strictly larger than the sum of the quadratic forms on the summands. Okay, and so this just gives you a way to pick out certain special roots. But this set really governs the combinatorics of the quiver variety then. Okay, so once you define this set, this is the key definition. So I'm going to say that a representation type of my dimension vector alpha is this K tuple. And so what are the K tuples? Each element in the K tuple is a pair of a dimension vector in sigma together with a multiplicity. So just a positive integer. Such that when I sum up all of these things with multiplicity, I get back my alpha. Okay, so that's a definition of a representation type. And the key result, well, I guess it depends on many results, but the final part is due to Crawley-Bouvier, which says that the symplectic leaves inside our quiver variety are labeled by these representation types. Okay, so we're going to be looking for representation types for our dimension vector alpha. And the second part that allows us to look at these minimal degenerations is that locally, if I'm on one of these leaves L tau, which is labeled by this representation type, then locally my quiver variety looks like a sort of local quiver variety. So this new quiver variety here, so there's two things here. There's a dimension vector, which is just encoding these multiplicities. So that's quite easy to write down. And then there's the new local quiver Q tau, sorry. So this new one you construct from this representation type. Your dimension vectors beta define for you the vertices of your quiver. So this new quiver has K vertices. And then the number of arrows between vertices is minus the Euler pairing of the dimension vectors. And then you also have to add in your loops. So your loops are just given by this P function. You just evaluate the P function on the dimension vector, and that tells you how many loops you have at each vertex. Okay, so that's an algorithm or a recipe, I guess, for cooking up this local quiver. And it's called the X quiver because this thing is really just the dimension of a certain X group between representations. Okay, so just to summarize, there's some combinatorial data that labels my leaf. And from that combinatorial data, you can read off locally what your quiver variety looks like. And that will give you the slice to that leaf then. Okay. Right. And so how do you get from that to the minimal degenerations? Well, there's a sort of key combinatorial lemma you need. The lemma is very easy once you realize it's the right thing to do. And it's sort of surprising that it's so easy, actually. So what you need to do is, maybe if I go back, so what this thing gives you is a way to reduce your question of minimal degenerations to just classifying minimal degenerations between your lowest leaf, your sort of closed leaf, and the next larger one. So instead of being somewhere in the middle of your Hesse diagram, you could reduce it to just looking at the very bottom. And so when it comes, oh no, sorry, I don't know this. When it comes to classifying that smallest minimal or the smallest non-zero leaves, what you need to really do is look at what are the possible minimal imaginary roots inside your root system. So by minimal imaginary root, I mean it's an imaginary root such that any root less than it has to be real. Okay, so these are all easy examples of minimal imaginary roots, and the non-triviality, of course, is that there's nothing else. So one example is if you just have a vertex with loops on it, then that simple root is minimal imaginary root. You, of course, have your minimal imaginary roots coming from affine dinking subquivers, which are what you would expect. And then finally, the one other example you get is if you have two vertices and many arrows between them, then this gives you a dimension vector 1, 1. So that is also a minimal imaginary root. And that's the only thing that can happen. And you see from each of these three minimal imaginary roots, you get the corresponding minimal degenerations then. So loops at vertices correspond to these strange ones, Cn and Mg. So Mg was this non-normal thing. Of course, these ones give you Kleinian singularities, and these give you the minimal nilpotent orbit closures of type A then. And as many of you, I'm sure, already know, so you can think of this as an analog of a result by Stembridge on minimal degenerations between dominant co-weights. Okay, that's how the sort of analogous result for affine Grassmannians comes about. Okay, and so once you have this lemma, the sort of classification follows very easily then from that. Okay. So this is just the basic sort of sketch of what you can do in examples. So I'm well aware that, the physicists have a very good algorithm to compute these things. We don't have an algorithm, we just sort of brute force on the computer, just do the combinatorics, and then you can work out, once you have all the leaves, what the minimal degenerations are. So essentially what you do is you just first work out what all these representation types are, and then you compute this X quiver for each leaf, and then you look at the minimal imaginary roots for that X quiver, and they tell you then what the minimal degenerations are inside your larger quiver. And let me just say, so how do I go from here to here? Well, the point is, if I have a root for this local or this X quiver, then just by using these beta i's in the representation type, I can use it to construct a root of my original quiver. And this sort of very simple idea gives you the way to go between leaves inside your local quiver back to leaves inside your larger quiver. Okay, so there's a sort of process you can go through. Right. So here's the more interesting thing. So some examples. Right, so I just sort of picked this quiver at random slightly. And you ask the computer, and it'll tell you that the corresponding Hesse diagram looks like this. So of course, this is just the dimension of the leaves going down. Oh, my pen's run out. Oh no. So, yeah, on the right-hand side, we have the dimensions of the leaves, and then I've just labeled each leaf Li. And the key thing, of course, is that the blue edges tell you what the minimal degenerations are between the leaves. So in this example, you can see at the very top, you've got a Kleinian singularity of type D4. Then you've got lots of A1 Kleinian singularities. And maybe the one interesting thing is that between leaf L2 and L4, there's a non-normal degeneration. So this tells you in particular that if I take this leaf L2, which is on the left-hand side, if I take its closure, that's going to give me a non-normal leaf closure then, because it's already non-normal in codimension 2. Okay, so yeah, this is one example. I wanted to give this example because there's also kind of an amazing additional fact about this example, which I will tell you. Oh, sorry, before then, sorry, I just want to describe the X quivers you get from this. Okay, so this is the same Hesse diagram, but now for each leaf, I've described for you what the corresponding X quiver looks like. So at the very top, you can see this is the open leaf, so this is smooth. And so the quiver you get has just got a single vertex and 4 loops. and a 1 at that thing. So that's just affine space. That just looks like C8. And then as you go down, your quivers start to get more and more complicated. So you can see just below the open leaf, you've got this affine D4 diagram with the loops. Basically, the loops are telling you the smooth direction along the leaf, so you can ignore those. And so you just get a Kleinian singularity of type D4. And you go on like that. So that's just an illustration that you can write down all of these local quivers for these examples. Okay, so the thing I wanted to say also about this example is, so I'm afraid I haven't got time to define this, and this is slightly tangential to the talk, but I wanted to say it for this example anyway, because I thought it was quite interesting. So to each one of these quiver varieties, you can associate a Namikawa-Weil group. You can do this more generally for any conic symplectic singularity. But in this case, these Weil groups are given by looking at the codimension 2 leaves inside your symplectic singularity. And so if I just go back for a second to the original Hesse diagram, there's a single codimension 2 leaf in this example, and it's transversely a D4 singularity. So the Weil group you would expect would be the Weil group for the Kleinian singularity, for the D4 Lie algebra. But in fact, when you compute this example, what you find is that there's a folding. So in fact, the Namikawa-Weil group for this particular example is actually G2 rather than D4, which is quite amazing, I thought. But I should point out that actually there's also a separate example by Wu where he gives a different quiver, which also has a G2 Weil group. And this is quite rare. So I should say that if I go back to the dimension vector, I actually checked all dimension vectors up to 10, 10, 10. So about 1,000 dimension vectors. And this is literally the only one in that set that has a Weil group, which is not A1 or A1 cross A1. So it's a particularly special example. And one of the implications of this is that for this quiver variety, there's a unique symplectic resolution. I mean, that's not immediate from what I'm saying. You have to do a bit more work, but that's what you find with this example. Okay. So any questions on that? Right, so here's a similar example. So again, I just sort of picked a 3-vertex quiver at random and started looking at dimension vectors. So you'll see here that, you've got 8 leaves in this example. You've got lots of these minimal degenerations of type A appearing. And here's one of these sort of exceptional examples appearing. So that's a type C minimal nilpotent orbit closure appearing. And so you just go through and you just ask the computer and it'll produce these Hesse diagrams for you. Yes. So, well, let me just do an example. Well, actually, no, let me do it in general. So you look at ways you can split up your representation type. So you're looking at things which are above it, but minimally above it. So if I have a situation like this, then one way I can create things that lie above it is I can split my n. Okay, and so the way you split your n is you could do it like A, beta, B, beta, and then the rest continue. Okay, so this is going to be a leaf which is above this. It's above this leaf and it's minimally so. Okay, and now type C or non-normal ones you get depend on the A and B. So if for A is equal to B, this minimal degeneration is C something, it depends on your beta, Cn. So when A is not equal to B and you do this sort of splitting of your N, what you get is this non-normal example, Mg. And the proof is really you just look at functions. So you look at the leaf closure and you look at what happens when you evaluate functions from your whole quiver variety on this leaf closure, and you get almost all functions, but not quite all. And so, sorry, I should say this better. You take the normalization of the leaf closure, and then you look at the map, restrict functions from your whole quiver variety to the normalization of the leaf closure, and don't get all functions. So that tells you that the leaf closure can't be normal. So it's some very explicit computation with functions. So hopefully that partially answers your question. Just to say that the most typical example of this splitting is if you just take a single vertex, put a dimension vector at least 2, and have at least, well, let me put an n there. And so say G vertices, then the minimal degenerations from 0 in this example would all look like these type Cn or Mg. So the sort of typical example of this behavior. Okay. So this is another example which I stole from the physics literature. So this comes from a paper by Gruminger and Hanani. And so they look at this framed quiver with this dimension vector, and they write down both the Hesse diagram for the Coulomb branch and for the Higgs branch. And so if you just do this algorithm, it sort of matches up with what they have in their paper, and you get this particular Hesse diagram for the quiver variety. And they explain that you can go from this to the Coulomb branch by doing this inversion. So you invert your Hesse diagram, and then you swap capital letters with lowercase letters. So again, as you can see, because this is a framed type A quiver variety, you get lots of type A singularities appearing in the example. Okay. So this is just another example. This was explained to me by Hanani. This is a really beautiful example, actually. It's very surprising. So it's surprising for 2 reasons. So one is, of course, the Hesse diagram is linear, which is very surprising compared to all the other examples. But also what you get is just a whole bunch of Kleinian singularities. So you have this whole tower of type D Kleinian singularities that get sort of smaller and smaller and smaller in rank. But then at the very bottom, you've got an E8 Kleinian singularity. And again, you can just use the combinatorics of the quiver and the root system, and you can just compute all these representation types, and you get out this Hesse diagram. Okay. So that was one example. Yeah, this is maybe my favorite example. So this actually is an example of what I was trying to say earlier about how to get these non-normal or these type C leaf closures. So if we just take a single vertex and lots of loops, so in this case 3 loops and a dimension vector 4, then this recaptures somehow the worst possible behavior. Okay, so you get lots of these, well, actually in this case only 2, but you get these non-normal minimal degenerations, and then you get lots of these type C minimal degenerations appearing as well. Okay, so the diagram starts to get quite complex. Okay, so I think that was the last example. So in the last 5 minutes, let me just say something briefly about normality of leaf closures. Okay, So the obvious question is, if I take one of these leaves now inside my quiver variety and I take its closure, do I get something which is normal? And of course, this is entirely by analogy with the case of orbit closures. This is why Kraft and Puchesi were studying these minimal degenerations in the first place, is because they tell you something about normality of orbit closures. So when you start thinking about this, the thing that's obvious is that the normalization is essentially always a quiver variety. The almost is just there because you have symmetric powers of quiver varieties, and it's not always the case that a symmetric power of a quiver variety is a quiver variety, but I mean essentially it's a quiver variety. But then the question is whether that normalization is actually the leaf closure itself, and we don't yet have a complete answer to this, but we have a very strong necessary condition. So I have to make this slightly strange definition. I'm going to take a pair of imaginary roots which are not equal, so beta and beta prime, inside this special set sigma, and I'm going to say that they have a real intersection if whenever I have a root which is less than beta and beta prime, so it sort of lies inside their intersection, and this root belongs to sigma as well, then that has to be real. Okay, so basically it's saying that there is no imaginary root inside sigma which is less than both beta and beta prime. Okay. And so when I look at my leaf closure, right, so remember this tau, it's labeled by these strange pairs, so N1 beta 1 up to N beta K. And so I look at this data, and if this is normal, then whenever I have a pair of beta I which are imaginary and equal, then these coefficients have to also be equal. I should say that there's a very nice interpretation of this. You can think of these taus as being colored partitions. So if you think of tau as assigning to every vector inside here a partition, then this first part is telling you that the partition assigned to beta has to be a rectangle. So that's the first condition. And then the second condition says that if I have a pair of non-equal imaginary roots, then they have to have this real intersection property. Okay, so when you start to write down examples, these are very strong restrictions. And so what you find is that actually most leaf closures are not normal inside these quiver varieties. Okay, so somehow that's the bad news. But in many cases, though, you can show that leaf closures are normal. And so let me give one sort of easy example. So if I have some tau where the first coefficient is 1, and I assume that every other beta that occurs is a real root. So somehow when you come to look at these leaf closures, the real roots really don't play a role. You can essentially ignore them, which is why we can do this. In that case, the leaf closure is normal. And the reason that this is kind of a useful fact is that if I take any finite type quiver, ADE quiver, with the framing, then my representation types will always be of this sort. And in that case, your leaf closure is always normal. And so this tells me that if you have a framed finite type quiver variety, then the leaf closures are always normal varieties. Okay, but as soon as you go to affine type framed, this will fail. And let me just give you a very, very quick final example. So what's the simplest sort of affine quiver? I guess you can just take a single loop and an N, right? So this gives you symmetric power of C2. And here the representation types are all just given by partitions of N. And so what our result tells you in this case is that the leaf closures here are normal if and only if lambda is a rectangle. Now, this is quite an easy result. You can just prove directly. You don't need the machinery for that. But if you apply this result in that case, you get that special statement. Okay, so I should finish there.